Okay, TMAT108 students, let's go ahead and start reviewing for our Unit 1 test. So these are some of the questions that are on the review handout of just some of the things that were in chapters 5, 6, and 8. So chapter 5 was over polynomials and their operations, so adding, subtracting, multiplying, dividing polynomials. Chapter 6 was over solving linear equations and using inverse operations and formulas and things like that. And then chapter 8 was over graphing lines. So these questions are not in any particular order, they're just random questions from some of those topics. So the first question says perform the operation, and then it has 4x squared and then parentheses 4x squared plus 3x plus 2. So that 4x squared that's sitting outside the parentheses needs to multiply by the polynomial on the inside. So we're going to distribute that 4x squared. The first distribution is 4x squared times 4x squared. So when we're multiplying, we don't have to worry about like terms. Multiplying, you can shove anything together, but then you typically will get a shift in the exponents. For variable pieces, they have the same base. How we put them together is we add the exponents. So on the first distribution, 4 times 4 is 16, and then x squared times x squared is going to be x to the 4th power. We're going to add those exponents. On the second distribution, 4x squared times 3x is going to be 12x cubed. So 2 plus, and then the assumed exponent right here is a 1. So 2 plus 1 is 3, is how I get the exponent on my new term. And then on the last distribution, I'll have 4x squared times 2, which is plus 8x squared. So my final answer is 16x to the 4th plus 12x cubed plus 8x squared. Question number 2 asks me to simplify 4 parentheses x minus 2, close the parentheses, minus 3 parentheses 2x minus 6, close the parentheses. In order to put these like terms together, we're going to have to distribute through and break those parentheses. On the first distribution, we will get 4x minus 8. On the second distribution, not only do I have to distribute the 3, but I also have to distribute the subtraction. So on my first distribution, I can think about it as being negative 3 times 2x. So a negative times a positive is a negative. 3 times 2x is 6x. On the second distribution, a negative times a negative is a positive, so I'll record a plus sign. And then 3 times 6 is 18. Putting my x terms together, 4x minus 6x is negative 2x. And then putting my constants together, negative 8 plus 18 is positive 10, which I'll record as plus 10. So the final answer is negative 2x plus 10. For question number 3, I'm given solving 3x minus 4y equals 10 for the variable y. So if I want to solve this for the variable y, that means everything else on that side I want to move to the other side. So the first thing I'm going to move to the other side is the 3x term, and I'll move it by subtracting it. So then I'll get negative 4y is equal to 10 minus 3x. Or you could write it as negative 3x plus 10, but I'm just going to write it in the order that I'm seeing it. Then to get that negative 4 away from my y variable, we'll divide everybody by negative 4. And that means we'll divide each individual term by negative 4. So over here on the left-hand side, the negative 4's will cancel, and I'll just have my variable y. And then on the other side of the equal sign, 10 divided by negative 4. So positive divided by negative is negative, and then 10 divided by 4 doesn't divide nicely, but I will record it as a fraction in simplified form. 2 goes into both of those numbers, so that simplifies to 5/2. On the next piece, a negative divided by a negative is a positive, so I'll record a plus sign. And then 3 divided by 4 does not divide nicely, so I'll just leave it as 3/4 and then x. We can either leave the x off to the side, or you could leave the x in the numerator. But we generally will write it off to the side, so that way we can see who the coefficient of that variable x is. And by the way, taking an equation like this and solving it for the variable y is how we would take a linear equation in 2 variables and write it in what is called slope-intercept form. in order to be able to read off some really important information about the equation, specifically its slope and its y-intercept. And speaking about slope-intercept form and using for graphing, the next questions will involve graphing. So the first equation I want to graph is x plus 3y is equal to -6. Now there's a couple different ways that I could go about graphing this equation. Just basically any equation that you're given, if you want to find the graph of the equation, you can just find some ordered pair solutions. So you typically would pick a value for one of the variables, you'd plug that value in, and then you find out what the corresponding other variable needs to be in order to make the equation true. Some special ordered pairs that we like to find on equations are the x-intercept and the y-intercept. To find the x-intercept, we would let the y value be 0 in the equation, and we will find the corresponding x value. So looking at this equation, if we let the variable y be 0, that means this whole term would go away because 3 times 0 would just be 0. And so I would have x is equal to -6. So that finishes my ordered pair. And then I could go ahead and plot it on my grid. -6, 0 on a coordinate axes will be -6 on the x-axis and 0 moving on the y-axis. If I want to find the y-intercept, I would let the value for x be 0, and I would find the corresponding value for y. So if I let x be 0, then I would have 3y is equal to -6, which means y has to be -2. So that finishes my ordered pair that I could go ahead and then plot on my coordinate grid. The ordered pair 0, -2 is 0 moving on the x-axis and then down 2 points on the y-axis. And we can find some other ordered pair solutions. So just another one that I had found was the ordered pair, for instance, like 3 and -3. If I go ahead and plot that, you'll see it still falls in the line or the trend that I've already been building. So you don't necessarily need to find these very specific ordered pairs. You could just find some solutions, but intercepts are usually good ones to find. The other way that you could graph this is you could put this equation into slope-intercept form, and you can use the slope to help you find other ordered pairs. So to put this thing into slope-intercept form to solve for the variable y, the first thing I'm going to do is I'm going to move x to the other side. So then I would have 3y is equal to -6 minus x, and then I would divide everybody by 3. So then I get y is equal to -2, and then this term right here, as opposed to writing it as x divided by 3, we'll write it as minus and then 1/3 x. So we can take that x and shove it off the shelf and write it off to the side, and then I'll put a 1 right here as a placeholder. The reason why we would want to do that is because the slope is the number that is sitting in front of your variable x, and the number that is sitting in front of my variable x is the -1/3. That slope tells me directions on how to get to other ordered pairs. So for that negative, you can either assign it to the numerator or you can assign it to the denominator. If I assign the negative to the numerator, so I'll have -1/3, this means from any point, if I go down 1 and right 3, I will get another ordered pair on my line. So for example, from 3, -3, if I go down 1, and write 1, 2, 3, I'll get another ordered pair that's on my line. If I assign the negative to the denominator, so I'm looking at 1/-3, this means from any point, if I go up 1 and left 3, I will find another ordered pair on my line. So for example, from the ordered pair 0 and -2, if I go up 1 and left 1, 2, 3, I will get another ordered pair solution on my line. And I can use this slope then to get a whole bunch of ordered pairs that then I could go ahead and connect. So let me go ahead and connect these. You should be using a ruler to draw these, and your line should extend all the way across whatever grid you are provided. Typically you'll be provided what's called a 10 by 10 grid, which means it goes from -10 to +10 on the x-axis and -10 to +10 on the y-axis. Right, so there is my completed graph for that equation. The next example, the equation is x is equal to -3. Now we typically would not think about this as being an equation involving x and y unless I know I'm working in that type of situation. So notice that this equation only tells me something about what the x-coordinate has to be in any ordered pair solution. It doesn't tell me what the y-coordinate has to be. So the y-coordinate then can be whatever it wants to be. As long as in my ordered pair the x-coordinate is -3, it will be a solution to this equation. So for instance, the ordered pair -3, 0 is a solution to this equation. The ordered pair -3, 4 is a solution to this equation. As long as the x-coordinate is -3, it's a solution. If I go ahead and plot those two ordered pair, -3, 0 and -3, 4, we only need 2 points to graph a line. So if I go ahead and connect those 2 points, we can see that we will end up with a vertical line. Another way to think about graphing these types of lines is if on the x-axis I go to -3, so here's the tick mark for x equals -1, here's the tick mark for x equals -2, here's the tick mark for x equals -3. The x equals -3 tick mark, if you just extend it, there's the graph of your line. So sometimes those are so easy, they're hard, because we're used to seeing two variables, and in this case we only have the one. Alright, let's take a look at a couple of other review problems. On the next one, we are asked to perform this operation. So 2x squared plus 3xy minus 5x all over, or divided by, 6xy. So in this case, we are dividing by a monomial. There is only a single term down here. In order to do this division, we're actually going to do a series of simplifying. That we're going to break this up into a series of fractions, where each of the numerator terms is going to be over that 6xy monomial from the denominator. All right, fraction operations tell me that this is a valid thing to do. Again, if I go back and forth, I'm saying these two expressions are equal or equivalent. And if we think about it, it's because over here, notice you have a common denominator. So the fraction rule says if you have a common denominator, you can apply the operation to the numerator, and then the common denominator gets like dragged through. And notice that's exactly what I would get for my starting expression. Now the reason why I would want to explode it out like this is because we are going to simplify term by term. Now just to be very clear about exactly how things simplify for that x squared, I'm going to explode that out and write it as x times x. So as I look at these fraction pieces that I have, if I see the same thing both upstairs and downstairs, we can cancel it or simplify it. So on the first fraction, the 2 and the 6 does simplify. 2 goes into itself once and into 6 3 times. And then I'll also have an x that'll cancel. On the second term, the 3 and the 6, 3 goes into itself once and into 6 2 times. The x's will cancel, the y's will cancel. On the last term, I'll have these x's cancel. So when I'm all done with my canceling, what I have left is on the first fraction, I'll have 1 times x, which I can just write as x. And then in the denominator, I'll have 3 times y, which I can write as 3y. On the second term, everything in the numerator canceled, but I have to leave something up there, so I'll leave a 1 as a placeholder. And then the downstairs, I'm just left with the 2. So my second term is plus 1/2. And then the last term, I have a negative divided by a positive, so it'll be negative. In the numerator, I have 5. In the denominator, I have 6y. And then that would be my final answer where I have simplified each piece. All right, on the next example, we are asked to perform this operation. So it's parentheses 6x cubed plus 3x squared plus 1, close the parentheses, minus parentheses negative 3x cubed minus x squared minus x minus 1. So I'm going to be working with two polynomials, and the operation between the two polynomials is subtract. So in order to subtract these polynomials, what we're going to have to do with this subtraction is we'll have to distribute it through that second polynomial, and by doing so, everybody will change its sign. The first polynomial, I could end up dropping the parentheses. They really aren't needed. So I'll have 6x cubed plus 3x squared plus 1. But as I distribute the subtraction through, I will then get plus 3x cubed plus x squared plus x plus 1. Now that I have broken all my parentheses and distributed the subtraction through that second polynomial, let's go ahead and start collecting our like terms. So I have a 6x cubed here and a 3x cubed here. When I put them together, I get 9x cubed. Remember, when you put like terms together, your result will look like the terms that you started with. I have x squared terms right here and here, so 3x squared plus another x squared is plus 4x squared. I have an x to the first power term right here, but I don't have anybody to go with it, so I'll just write that one next. So I like to collect my powers of x first, and then I'll write the constant or the number part last. So I have a number part here, this plus 1, and then a plus 1 right here. When I put them together, I'll get plus 2. So the final answer is 9x cubed plus 4x squared plus x plus 2. On the next one, I was asked to determine if the lines are parallel, perpendicular, or neither, and we're going to answer this question by using the argument for slope. So if the lines are parallel, they're going to have the same slope. If the lines are perpendicular, that means that the slopes will multiply together to give me -1. And if neither one of those things are happening, then the conclusion is neither. The two equations I was given was 6x minus 9y is equal to 12 and 4x minus 6y is equal to 18. Neither one of these equations are in slope-intercept form. In other words, neither one of these are solved for y. So I can't read off my slope information right now in the form that they're in. There's a couple different ways to recover the slope. I think the easiest way is let's just go ahead and put them into slope-intercept form. So for the first equation, the 6x minus 9y is equal to 12. To put this thing in slope-intercept form, first we'll move the 6x to the other side by subtracting it. So I get -9y is equal to 12 minus 6x. And then we'll divide everybody by -9. So I get y is equal to, all right, so 12 divided by -9 doesn't divide nicely. So I'm going to write it as a fraction. Positive divided by a negative is negative, and then 12/9 simplifies to 4/3. On the last piece, I'll have a negative divided by a negative, which is a positive, and then 6 divided by 9 doesn't divide nicely, so the simplified fraction there would be 2/3. And then I'm going to write the x off to the side. So this guy's slope, which is the number in front of the variable x, is positive 2/3. All right, we'll keep that in mind as we go to find the slope of the other line. All right, so let's go find the slope of 4x minus 6y is equal to 18. To solve this for the variable y, we'll move the 4x to the other side by subtracting it. So I get -6y is equal to 18 minus 4x. And we'll divide everybody by -6. So I get y is equal to, so a positive divided by a negative is negative, and then 18 divided by 6 is 3. On the last term, a negative divided by a negative is a positive, and then 4 divided by 6 does not divide nicely, so I am going to simplify that fraction to 2/3, and then the x I'm going to write off to the side. So the slope of this line, which is the number in front of the variable x, is 2/3. So the first line had a slope of 2/3, the second line had a slope of 2/3, so then we conclude that these lines are parallel. In the next example, we are asked to perform this operation, parentheses 9x minus 1, close the parentheses, new parentheses, x squared minus 2x plus 1. Because these parentheses are touching each other, that is going to tell me that the operation right here is multiplying. To multiply, we're going to distribute every term and multiply it by every other term. To help keep track of how many distributions that we have to do, there is a cool model we can use. It's called an area model. And how it works is we're going to draw a rectangle on one side of the rectangle and break it up into two pieces to account for the two terms in that first parentheses expression. And then the other side of the rectangle, I'm going to break it up into three pieces to account for the three terms in the other polynomial expression. So I'm going to go sketch a rectangle, and this side I'll break it up into two pieces, and this other side will break it up into three pieces. So next to each small piece, I'm going to write what the term is. So my first polynomial was 9x and then minus 1. So my two terms are written next to those side pieces, 9x and then negative 1. Across the top, I'll write x squared and then minus 2x and then 1. You could write plus 1, but I'll just leave it as 1. Notice that all for the negative terms, we always keep the sign in front of the term. So for the subtraction, we ultimately will record those as negatives when we kind of do this explosion or this breaking apart. So now my goal is we are going to find the area of each box. Remember how to find the area of a rectangle is its length times its width. So this first box has an area of x squared times 9x, which would be 9x cubed. The second rectangle has an area of negative 2x times 9x, or negative 18x squared. This third rectangle across the top row is going to have an area of 1 times 9x, or 9x. And now I have finished three distributions. Let's go ahead and multiply negative 1 by everybody. So negative 1 times x squared is negative x squared. Negative 1 times negative 2x is positive 2x. If you want, you can put the little plus sign right there, but I'm just going to write 2x. And the last distribution will be negative 1 times 1, or negative 1. So that keeps account of my distributions. Ultimately, I will have 6 distributions that I had to do, or 6 multiplications. So let's go ahead and start collecting the like terms. So I don't have any other cube terms, so I'll be left with 9x cubed. When I put my x squared terms together, I'll get minus 19x squared. If I put my x to the first power terms together, I'll get plus 11x. And then just the constant, or the number by itself, doesn't have anybody to pair with it, so it'll be minus 1. So then the final answer is 9x cubed minus 19x squared plus 11x minus 1.